Manipulation in human environments often requires coordinating the motion of two arms. However, such bimanual actions are challenging due to the high dimensional action space and the need for synchronizing both arms. One way to teach robots bimanual action is to teleoperate the robot to collect demonstrations. However, it is difficult to collect demonstrations for bimanual tasks, which often requires specialized hardwares. An easier and more scalable approach is to directly learn from human videos. But this is challenging as well due to the differences in morphology and the difficulty to cleanly parse the video to obtain robot actions. So how can we facilitate bimanual manipulation in robots? Our key insight is that several bimanual tasks can be represented as screw motions with a simple 1 degree of freedom screw axis as shown here. This virtual joint constrains the motion in a way that either matches an existing physical constraint in the environment or just facilitates the manipulation. This insight helps in several ways. First, in perception, the screw axis representation helps to cleanly parse human demonstrations, and secondly, in exploration, it provides a more efficient action space. Thus, we introduce ScrewMimic, a novel method that leverages this insight for one-shot visual imitation learning of bimanual manipulation from a single human demonstration. ScrewMimic works as follows. It first takes as input a single RGBD video of a human performing a bimanual manipulation task. It then extracts the contact locations for both the hands with a hand object detector and projects them into the 3D point cloud of the object P. ScrewMimic then uses an off-the-shelf hand tracker to obtain the trajectories of the human hands and infers the screw axis by analyzing the relative motions between them. Based on this information, ScrewMimic extracts a screw action, sigma, consisting of the left and the right hand contact locations and the screw axis, and a possibly additional left-hand trajectory. But we want a solution to generalize the perceived screw action to novel object instances and poses. How? In the second step of ScrewMimic, we train a model that predicts the screw actions from an object's point cloud. Thanks to the 3D nature of both the input observation and a screw action representation, ScrewMimic can learn to generalize based on a dataset of geometric augmentations of the single observed screw action and the corresponding point cloud from the demonstration. Due to the noises in the human hand tracker and the differences in morphology, the direct robot execution of the observed screw action may fail. Thus, we introduce a screw action policy fine-tuning module. For a new trial, the robot obtains an initial screw action and executes it. As shown here, ScrewMimic implements a self-supervised failure detection mechanism based on grasp loss and exceeding force detectors that informs the robot when a strategy fails. On the top left, we also show the norm of the applied forces over time as measured by a force torque sensor on the wrist. If the initial strategy fails, ScrewMimic implements an iterative refinement in the screw action space with a cross-entropy method. In each episode, a screw action is sampled from a distribution and a corresponding trajectory is executed and ranked based on a self-generated reward. This reward considers episode length, determined by grasp loss or reaching a force threshold as shown, and the mean force used. After ranking the episodes, the top episodes are chosen to update the sampling distribution after each epoch. The fine-tuning stage runs for 5 epochs and 5 epochs each and stops whenever a success is achieved. ScrewMimic then extracts the screw action from the successful strategy. The new successful screw action is further used to improve the prediction model as shown. We evaluate ScrewMimic on 6 real-world bimanual tasks as shown. We want to assess if a single human demonstration is enough for ScrewMimic to achieve success in bimanual manipulation tasks. Here you can see the result for stirring task. The robot first executes the initial strategy based on the predicted screw action and the prediction model. Since that fails, it employs the screw action fine-tuning stage. The robot explores by sampling different screw actions from a sampling distribution and updating it after each epoch. As the epochs progress, the sampled screw action brings the robot closer to achieving success, ultimately attaining it. ScrewMimic can achieve success in all bimanual manipulation tasks by watching a single human demonstration and subsequently performing real-world policy fine-tuning. We also explore if the screw action prediction model improves from robot interactions to reduce the need for new explorations. The picture shows predictions from a first model, M1 in red, trained with data from the human video compared to the predictions from second model, M2 in green, trained with the refined screw action after exploration. The second model provides more accurate predictions and generalizes better to unseen poses. Can ScrewMimic generalize to new objects? We evaluate the generalization of ScrewMimic to different instances of the same class. Depending on if the differences are larger, as in the bottle, or smaller, as in the roll, the amount of exploration for a new object may be more or less. But in any case, ScrewMimic is able to manipulate these completely new objects. Moreover, after interacting with them and retraining, it succeeds almost zero shot to those new objects. While in our experiments, we focused on the relative motion between the hands and did not consider the absolute motions of both, our method is general enough to cover any absolute motion. Here we show an example of the stir task with a left hand trajectory. Because the screw action focuses on the relative axis between hands, it generalizes to any single hand absolute motion. In summary, ScrewMimic shows how various bimanual actions can be represented by a simple 1 degree of freedom screw joint, how the screw action representation helps in a more accurate human demonstration interpretation and efficient exploration for the robot, and finally, how ScrewMimic can continually expand its manipulation capabilities to new objects. Thank you.